Now in this lecture I will answer two questions. In the first question we will find out the size of this angle ABC is equals to x. We have to find out the value of angle x. And in the second question we will find out the length of this line segment AD is equals to x. So we have to find out the value of line segment x. So we start with the first question. In the drawing we have quadrilateral ABCD. Those two angles are both equal to 80 degrees in their sizes. In addition, we know that AD equals to AB equals to BC. Again, our task is to find out the size of this angle ABC is equals to x. So we have to find out the value of this angle x. So first of all, we will join points B and D together by a straight line. By joining points B and D, we divided this quadrilateral ABCD into two triangles. We have the upper triangle BCD and the lower triangle BAD. We know that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in triangle BAD, we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle ABD is alpha, then the size of this angle ADB must be also equal to alpha according to the order dimensions. In front of equal sides in the triangle there are equal angles. We know that the sum of the angles in any triangle is equal to 180 degrees. So in triangle ABD, alpha plus alpha is 2 alpha plus 80 degrees. In total, the sum of those angles must be equal to 180 degrees according to the order dimensions. So already know in triangle ABD, two alpha plus 80 degrees total the sum of those angles must be equal to 180 degrees. And again, in triangle ABD, the lower triangle ABD, 2 alpha plus 80 degrees must be equal to 180 degrees. Here we subtract 80 degrees from this equation, and we will get that 2 alpha equals to 180 degrees minus 80 degrees is 100 degrees. So 2 alpha equals to 100 degrees. Here we will divide this equation by 2. And finally we get that the missing angle alpha is equal to 100 degrees over 2 is 50 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 50 degrees in size. What is the size of this missing angle, angle BDC? From the drawing it is very easy to see that the missing angle BDC equals to 80 degrees minus 50 degrees. Again, the missing angle BDC equals to 80 degrees minus 50 degrees, that is 40 degrees. So angle BDC equals to 30 degrees in its size. In the next step, we will define this angle BCD as beta. And we will implement the law of sines in this triangle ABD. So a bit quickly on the law of sines. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. AB equals to C units in its length, AC equals to B units in its length, BC equals to A units in its length. Likewise, this is angle BAC that is equals to capital A degrees in its side. This is angle ACB that is equals to capital C degrees in its size. And this is angle ABC that is equals to capital B degrees in its size. So in this triangle, like ABC that could be any triangle, according to the law of sines, the following equation is true. A over sinus A equals to B over sinus B equals to C over sinus C. Again, this triangle ABC that could be any triangle, the following, according to the law of sines, the following equation is true. A over sinus A equals to B over sinus B equals to C over sinus C. So can implement the law of sines in our drawing. Actually, we will implement the law of sines. First of all, in this triangle ABD, and then we implement the law of sines in this upper triangle BCD. So first of all, we will implement the law of sines in this triangle ABD. According to the law of sines, this triangle ABD the following equation is true. BA over sinus 50 degrees equals to BD over sinus 80 degrees. Repeat again, according to the law of sines, this triangle ABD, the following equation is true. BA over sinus 50 degrees equals to BD over sinus 80 degrees. It is given us the question that AB equals to AD equals to BC. So if we define the law for side BA as A, then side BC must be also equal to A, and side AD must be also equal to A because they are equal to each other. All those three sides, AD, AB, and BC are equal to each other according to what is given in the question. So if you remember that according to the law of sines, BA over sinus 50 degrees equals to BD over sinus 80 degrees. BA is A according to our definition, so we substitute BA by A. And we have here sinus 50 degrees. We substitute 50 degrees by 90 degrees minus 40 degrees. With again, we substitute 50 degrees by 90 degrees minus 40 degrees. So sinus 50 degrees equals to sinus 90 degrees minus 40 degrees. again, sinus 50 degrees equals to sinus 90 degrees minus 40 degrees, and is equals to BD over sinus 80 degrees. Here we substitute 80 degrees by 2 times 40 degrees. Again, we substitute 80 degrees by 2 times 40 degrees. So sinus 80 degrees equals to sinus 2 times 40 degrees. So in total, we should find out that according to the law of sines, in triangle ABD, A over sinus 90 degrees minus 40 degrees equals to BD over sinus 2 times 40 degrees. Here we will use two trigonometric identity, and we will implement the two trigonometric identities in our equation. The first trigonometric identity is as follows. Sinus 2 alpha equals to 2 times sinus alpha cosine alpha. And again, the first trigonometric identity says that sinus 2 alpha equals to 2 times sinus alpha cosine alpha. And the second trigonometric identity is as follows. Sinus 90 degrees minus alpha equals to cosine alpha. So we implement those two trigonometric identities in our equation. The first trigonometric identity is sinus alpha equals to 2 times sine alpha cosine alpha. The second trigonometric identity is sinus 90 degrees minus alpha equals to cosine alpha. So in our equation we have A or sinus 90 degrees minus 40 degrees. Sinus 90 degrees minus 40 degrees according to this trigonometric identity is cosine 40 degrees. According to the second trigonometric identity. So we have here A over sinus 90 degrees minus 40 degrees is cosine 40 degrees according to the second trigonometric identity. And it is equals to BD. BD is the missing side, so leave it as it is. Over sinus 2 times 40 degrees. According to the first trigonometric identity, sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. So in total, we have found out that A over cosine 40 degrees equals to BD over 2 times sinus 40 degrees cosine 40 degrees. Here we have cosine 40 degrees on both sides of this equation, so cosine 40 degrees will get cancelled. I'll take cosine 40 degrees. In this side of the equation we left only with A, while on the other side of the equation we left only with BD over 2 times sinus 40 degrees. So in total we found out that A equals to BD over 2 times sinus 40 degrees. Here we multiply this equation by 2 times sinus 40 degrees. And we get that the missing side BD is equal to 2A sinus 40 degrees. And again, this is the missing side BD. That's equal to 2A times sinus 40 degrees. So write it down. BD equals to 2A times sinus 40 degrees in its length. In the next step, we will implement the law of sines. This upper triangle BCD. Again, we implement the law of sines in this green triangle, triangle BCD. The upper green triangle, triangle BCD. According to the law of sines, in this upper green triangle, triangle BCD, the following equation is true. BC over sine of 30 degrees equals to BD over sinus beta. And again, in this green triangle BCD, according to the law of sines, the following equation is true. BC over sinus 30 degrees equals to dP over sinus beta. We already found out that BD of dB is equal to 2A sinus 40 degrees. So we substitute BD by 2A times sinus 40 degrees, and BC equals to A. So we substitute BC by A. So we get that BC is A over sinus 30 degrees. Sinus 30 degrees is 1/2. So we substitute sinus 40 degrees by 1/2. And is equals to BD. BD is 2A times sinus 40 degrees over sinus beta. This side of the equation we have 2 over 1/2. 2 over 1/2 is 2A. And in the other side of the equation we have 2A times sinus 40 degrees over sinus beta. Here we will multiply this equation by sinus beta, and we get that 2A times sinus beta equals to 2A times sinus 40 degrees. We have 2A on both sides of this equation, so 2A will get cancelled. Of the cancelled 2A, we left only with sinus beta equals to sinus 40 degrees. If sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees. Again, if sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees in its size. This is the first solution for beta. And the second solution for beta is as follows. Here we do third trigonometric identity. According to the third trigonometric identity, sinus alpha equals to sinus 180 degrees minus alpha. And again, according to the third trigonometric identity, sinus alpha equals to sinus 180, sinus alpha equals to sinus 180 degrees minus alpha. According to this third trigonometric identity, we will get that sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. But again, according to this trigonometric identity, sinus alpha equals to sinus 180 degrees minus alpha, we get that sinus 40 degrees equals to sinus 180 degrees minus 40 degrees. So sinus 40 degrees equals to 180 degrees minus 40 degrees is 140 degrees. So we should find out that sinus 40 degrees equals to sinus 140 degrees. And again, we should find out that sinus 40 degrees equals to sinus 140 degrees. But we already found out that sinus beta equals to sinus 40 degrees. So as we know, we already found out that sinus beta equals to sinus 40 degrees. Or sinus 40 degrees equals to sinus beta. That is what we already found out. And we just right now found out that sinus 40 degrees equals to sinus 140 degrees. So we can add in this equation that sinus 40 degrees is equals to sinus 140 degrees. And from this equation, sinus 140 degrees equals to sinus 40 degrees equals to sinus beta. We will derive that sinus beta equals to sinus 140 degrees. Those two sides of the equation are equal to each other. So sinus beta equals to sinus 140 degrees. If sinus beta equals to sinus 140 degrees, it means that beta equals to 140 degrees. Beta equals to 140 degrees in each side. That is according to the second solution for beta, but according to the first solution for beta, we only found out that beta equals to 40 degrees in each side. So we have two solutions for angle beta. Beta could be equal to either 40 degrees or could be equal to 140 degrees. But if you focus on the green triangle BCD, this is angle beta. From the drawing it is very easy to see that angle beta is definitely greater than 90 degrees. If beta is greater than 90 degrees, it means that beta can never be equal to 40 degrees, that is less than 90 degrees. So the first solution for beta is incorrect solution according to the drawing. We can set the first solution for beta and we left only with the second solution for beta. That's actually beta equals to 140 degrees in its size. So in the next step, we focus on this green triangle BCD. In the green triangle BCD, the sum of the areas must be equal to 180 degrees according to the rule that the sum of the areas in any triangle is equal to 180 degrees. So which angles we have on the green triangle BCD? We have this angle that is 30 degrees plus angle beta equals to 140 degrees in its size plus this first missing angle is actually angle DBC. In total, the sum of those two angles must be equal to 180 degrees. Okay, again, in the green upper triangle BCD, the sum of the angles must be equal to 180 degrees. That is to say, 30 degrees plus 140 degrees plus the first missing angle DBC in total must be equal to 180 degrees. 30 degrees plus 140 degrees is 170 degrees. So 170 degrees plus the size of the first missing angle is actually angle DBC. In total, the sum of those three angles must be equal to 180 degrees. So here we subtract 170 degrees from this equation, and we get that the missing angle DBC equals to 180 degrees minus 170 degrees is 10 degrees. This is the missing angle DBC, this equals to 10 degrees in its size. Our test is to find out this angle ABC, is equals to x. Angle ABC is equals to x, equals in total to 50 degrees plus 10 degrees, that is 60 degrees. So if you found out that the missing angle ABC is equal to x degrees in its size, is equal to 60 degrees. And again, this is the missing angle ABC. Angle ABC in total equals to 60 degrees in its size. Angle ABC equals to angle x, and is equals to 60 degrees in its size. So finish with the first question. The next step, I present you the second question, and we solve the second question by using two different methods. In this second question, our task is to find out the length of this side AD equals to x. So we have to find out the value of line segment x. So in the drawing we have quadrilateral ABCD. We know that AB equals to BP. The short line segment DP equals to 1 unit in its length. Line segment PC equals to 4 units in its length. Those two angles are both right angles. Again, our task is to find out the length of this side AD equals to x. So we have to find out the value of line segment x. So first of all, we will join points B and D together by a straight line. By joining points B and D, we divided quadrilateral ABCD into two right angles. The upper right angle is triangle ABD, this triangle, and the lower right angle is triangle DBC. So we will implement the Pythagoras theorem on both those two right angles in the first step. So first of all, we will implement the Pythagoras theorem on this upper right angle, triangle ABD. Here by PT is the prevention for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this upper right triangle ABD, BD square, that is the square of the hypotenuse, equals to AB square plus DA square or AD square. And again, in this upper right triangle BAD, according to the Pythagoras theorem, BD square, that is the square of the hypotenuse, equals to AB square plus AD square. BD is the missing hypotenuse, so we leave this it is. So it is BD square equals to AB square. AB is also the missing side, so we leave this it is. So it is AB square plus AD square. AD equals to x, therefore AD square is x square. AD is the side that we are looking for in this question. So AD square is x square. We have to find out the length of line segment AD is equals to x. So in total, according to equation 1, BD square equals to AB square plus x square. Likewise, we will implement the Pythagoras theorem on this right lower triangle DBC. Here by PT is the evolution for Pythagoras theorem. According to the Pythagoras theorem, in this right lower triangle DBC, dB squared, that is the square of the hypotenuse, equals to BC square plus DC square. And again, this right lower triangle DBC, according to the Pythagoras theorem, the following equation is true. dB squared, that is the square of the hypotenuse, equals to BC square plus DC square. dB is the missing hypotenuse, so we leave it as it is, so it is dB square equals to BC square. BC is also the missing side, so we leave it as it is. It's BC square plus DC square. DC in total equals to 1 plus 4, that is 5, therefore DC square is 5 squared, that is 25. So according to equation 2, we should find out in total that dB square equals to BC square plus 25. While according to equation 1, we only found out that dB square equals to AB square plus x square. So we have two different equations for BD square. Therefore, we get the equation 3 that said that BD square according to equation 1 must be equal to BD square according to equation 2. So I did not according to equation 3. BD square according to equation 1 must be equal to BD square according to equation 2. This is equation 3. So according to equation 3, BD square according to equation 1 equals to AB square plus x square. And it must be equal to BD square according to equation 2. BD square according to equation 2 equals to BD square plus equals to BC square plus 25. So total according to equation 3, I should find out that AB square plus x square equals to BC square plus 25. In the next step, we will implement the Pythagoras theorem on this triangle, right triangle BPC. In this green right triangle BPC or PBC. So according to the Pythagoras theorem, in this again arterial PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus PC squared. And again, according to the Pythagoras theorem, on this green triangle PBC, PB squared equals to BC squared plus PC squared. According to what is given as the question, PB equals to AB. PB equals to AB, so we substitute PB by AB, because they are equal to each other according to what is given as the question. So PB squared is AB squared. According to the equation 4, AB squared equals to BC squared. BC is the missing side, so related it is. So this is BC squared plus PC squared. PC equals to 4, therefore PC squared is 4 squared, it is 16. So in total, according to equation 4, we have found out that AB squared equals to BC squared plus 16. This is according to equation 4. And according to equation 3, we have already found out that AB squared plus X squared equals to BC squared plus 25. And again, according to equation 3, we already found out that AB squared plus X squared equals to BC squared plus 25. But according to equation 4, AB squared equals to BC squared plus 16. Therefore, we substitute AB squared in this equation 3 by BC squared plus 16 from equation 4. We do it now, we get it that according to equation 3, again AB squared is BC squared plus 16. We have in equation 3 plus X squared equals to BC squared plus 25. Here we have BC squared on both sides of this equation, so BC squared gets cancelled. After cancel BC squared, on this side of the equation we are left with 16 plus X squared. While on the other side of the equation we are left only with 25. So in total we found out that 16 plus X squared equals to 25. Here we subtract 16 from this equation 3. If I get that according to equation 3, X squared equals to 25 from 16 is 9. So X squared equals to 9. Here we take out of this equation. If I get that X equals to the square root of 9, that is 3. X equals to 3. So here side AD is equals to X. Side AD is equals to X is equals to 3 units in its length. So she found out that AD is equals to X is equals to 3 units in its length. So finish with the first method. The next step I will present to you how to find out the length of side AD is equals to X according to the second method. in the second method, we will do a construction. That is to say, we'll extend side DC of quadrilateral ABCD by 4 units. Again, we'll extend side DC of this quadrilateral ABCD by 4 units. And we will define the edge of this extended line segment. This point is point Q. So actually CQ equals to 4 units in itself according to our construction. Repeat again. The extended line segment CQ equals to 4 units in itself according to our construction. DC is one side of quadrilateral ABCD, so this is the side of a quadrilateral, it is absolutely a straight line. And when you extend a straight line by straight line, the result DQ is also a straight line. So DQ is a straight line. If you focus on the upper side of the straight line DQ at point C, here the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line DQ at point C? We have this angle that is a right angle. According to what is given as the equation, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will join points B and Q together by straight line. By joining points B and Q together and the right line BCQ. So in the next step, we will prove that those two right angles can point to each other according to side angle side rule. Again, we will prove that those two right angles, triangle PBC and triangle BCQ, can point to each other according to side angle side rule. So we have to prove that this is the right triangle PBC. So we have to prove that the right triangle PBC can point to this right triangle BCQ according to side angle side rule. So why those two right angles can go into each other? First of all, PC equals to CQ. Those two sides are equal to each other because of the fact that each side equals to 4, therefore they are equal to each other. So side PC on the right triangle PBC is equal to side CQ of the right triangle BCQ. Okay, again, if you hold on that side BC of the right angle PBC equals to side CQ of the right angle PCQ. They are both equal to 4 units and therefore they are equal to each other. Side CQ equals to 4 units in itself according to our construction. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually this is angle PCB in the right angle PBC, and it is equals to this angle. This is actually angle BCQ in the right angle BCQ. So repeat again, we should find out that angle PCB in the right angle PBC equals to angle BCQ in the right angle BCQ. They are both equal to 90 degrees and therefore they are equal to each other. And finally, this is side BC. This is the common side that belongs to both triangles. So we can find out that BC equals to itself is a common side that belongs to both triangles. And again, we should find out that side BC equals to itself is a common side that belongs to both triangles. So in total, we should find out that those two right angles can point to each other according to side against side rule. So I write it down. Right angle PBC can point this is the side can point to the right angle BCQ. According to side against side rule. That is to say, we have found out that those two sides and the angle that is included between those two sides, this angle PBC of course will equal to those two sides, and the angle that is included between those two sides, this right angle BCQ. And therefore those two right angles can point to each other according to side angle side rule. Repeat again that we have those two sides and the angle that is included between those two sides, this right angle PBC of course will be equal to those two sides, and the angle that is included between those two sides in this right angle BCQ. Therefore, triangle BCQ. Therefore, those two right angles can point to each other according to side angle side rule. And from the fact that those two right angles can point to each other, we will derive that their corresponding sides must be also equal to each other in their lengths. The two corresponding sides are the hypotenuses of those two right angles. That is to say, PB and BQ. So PB equals to BQ. PB equals to BQ according to the rule that said that corresponding sides and congruent triangles are equal to each other. Those two triangles can point to each other, and therefore their corresponding sides, that is to say PB and BQ, must be also equal to each other in their lengths. But according to what is given as the equation, AB equals to BP. So we can write that AB equals to PB, according to what is given as the equation. And from this equation, AB equals to PB equals to BQ, we will derive that all those three sides, AB, PB, and BQ, they are equal to each other in their lengths. Okay, all the three sides AB, PB, and BQ are equal to each other in their lengths. So in the next step, we will do a construction. That is to say, we will draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. Okay, again, we'll do a construction in such a way that we draw a circle around point B in such a way that the center of the circle will be at point B and the radius of the circle will be BA. Okay, again, actually constructed a circle around point B in such a way that point B is the center of the circle and BA is the radius of this circle. So we will define the radius of this circle BA as R, and because of the fact that we have already found out that BA equals to PB equals to BQ, BA equals to PB equals to BQ, and AB equals to R, and therefore PB and BQ must be also equal to R, because they are equal to each other. So PB equals to R, it is the radius of the circle, and BQ is also equals to R, is the radius of this circle. So what is the definition of a radius? The radius of any circle starts from the center of the circle and ends on the circle itself. Again, the radius of any circle starts from the center of the circle and ends at the circle itself. Therefore, point P must be located on the circle itself, point A must be also located on the circle itself, and point Q must be also located on the circle itself. Or in other words, the circle passes for points A, P, and Q. Again, because of the fact that those three line segments AB, BP, and BQ are all the area of the circle, it means that the circle must pass for point A, P, and Q. We know that according to what is given as equation, DA is perpendicular to AB. Why? Because angle DAB is a right angle, and therefore DA is perpendicular to AB. This is the sign of perpendicular, DA is perpendicular to AB. But according to our construction, AB is the radius of this circle. So I can write here that AB equals to R, which is the radius of the circle. So in total, we found out that DA is perpendicular to the radius R of the circle. DA is perpendicular to the radius R of this circle. Therefore, DA must be a tangent to this circle. So DA is a tangent to the circle, and the point of tendency of tangent DA with this circle is point A. So DA is the tangent to the circle at point A. This is the common standpoint point D. From the common standpoint point D, we have tangent DA, that is tangent to this circle at point A. Likewise, we have here secant dq. This is secant dq that cuts the circle at 2 points P and Q. So all the requirements of tangent secant theorem are satisfied, and therefore we can implement tangent secant theorem in our drawing. So a bit quickly on tangent secant theorem. It's only to tangent secant theorem if a tangent and the secant are drawn to a circle from the same external point. This is the common external point P. From this common external point P, we have tangent PA, that is tangent to this circle at point A. Likewise, we have from the same common external point P, we have secant PB that cuts the circle at 2 points B and C. And again, from the same common external point P, we have secant PC that cuts the circle at those 2 points B and C. So in this drawing, the following equation is true. The square of the tangent length equals to the product of the secant's all length and its external part. The square of this tangent is PA square. PA square equals to the product of the external part of secant PC, that is PB, times the length of the secant in total, that is PC. So PA square equals to PB times PC. So according to tangent secant theorem, PA square, that is the square of the tangent, equals to PB times PC. PB is the external part of secant PC, and PC is the length of the secant in total. So the product of the external part of the secant with the length of the secant in total is PB times PC, and it equals to PA squared, that is the length of the tangent squared. So we can actually implement tangent secant theorem in our drawing, as I already mentioned before. All the requirements of tangent secant theorem are satisfied, and therefore we can implement tangent secant theorem in our drawing. Then again, from the common external point D, we have tangent dA, that is tangent to this circle at point A. Likewise, from the same common external point D, we have secant dQ. Secant dQ cuts the circle at 2 points P and Q. So all the requirements of tangent secant theorem are satisfied, and therefore we can implement here tangent secant theorem. According to tangent secant theorem, dA squared, that is the length of the tangent squared, equals to dP times dQ. dA squared equals to dP times dQ. So according to tangent secant theorem, if we focus on the common external point D, the following equation is true. dA squared, that is the length of the tangent square, equals to dP times dQ. dP times dQ is the product of the external part of secant dQ, that is dP, times the length of the secant in total, that is dQ. And it equals to dA squared. dA squared equals to dP times dQ according to tangent secant theorem. dA equals to x, therefore dA squared equals to x squared. And it equals to dP. dP is 1 times dQ. dQ in total is 1 plus 4 plus 4, that is 9. So in total, if we found out that x squared equals to 1 times 9, that is 9. X squared equals to 9. Here we take all of this equation, and finally we get that x equals to the square root of 9, that is 3. So 9/7 AD or side AD is equals to x equals to 3 units in its length. So on both methods, we found out that the length of 9/7 AD is equals to x is equal to 3 units. So we finish with the second method, or the second question. In the next step, I will summarize the lecture. We'll start with the first question, with the repetition of the first question, and then we repeat on the solution of the second question on both methods. In the first question, our test was to find out the size of this angle ABC is equals to x. So we have to find out the value of this angle x. So in the drawing, we have quadrilateral ABCD. Those two angles are both equal to 80 degrees in their sizes. In addition, we know that AD equals to AB equals to BC. Again, our test is to find out the size of this angle ABC is equals to x. We have to find out the value of this angle x. So first of all, we join points B and D together by straight line. By joining points B and D, we divided this quadrilateral ABCD into two triangles. We have the upper triangle BCD and we have the lower triangle ABD. We have the rule that says that in front of equal sides in the triangle there are equal angles. Again, in front of equal sides in the triangle there are equal angles. So in triangle ABD, in front of those two equal sides, we have those two angles that are equal to each other, that must be equal to each other. So if we define this, the size of this angle as A, then the size of this angle must be also equal to A. If we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, according to the order dimensions. And we know that the sum of the angles in a triangle is equal to 180 degrees. So in triangle ABD, alpha plus alpha is 2 alpha plus 80 degrees, in total must be equal to 180 degrees. So in triangle ABD, alpha plus 80 degrees must be equal to 180 degrees. Here we subtracted 80 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees plus 80 degrees is 100 degrees. So 2 alpha equals to 100 degrees. Here we divided this equation by 2, and finally found out that the missing angle alpha equals to 100 degrees over 2 is 50 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 50 degrees in its size. In the next step, we implemented the law of sines. This triangle ABD. So application of the law of sines. The law of sines is true in any triangle. This is a triangle ABC that could be any triangle. The length of side AB is C units, side AC equals to B units in its length, and side BC equals to A units in its length. Likewise, this triangle BAC is equals to capital A degrees in size. This is angle ACB that equals to capital C degrees in size, and this is angle ABC that equals to capital D degrees in its size. So in this triangle ABC, that could be any triangle. According to the law of sines, the following equation is true: A over sinus A equals to B over sinus B equals to C over sinus C. Again, this triangle ABC, A over sinus A equals to B over sinus B equals to C over sinus C. So we can actually implement the law of sines in our domain, in triangle ABD. Implemented the law of sines, this triangle ABD. According to the law of sines, in this triangle ABD, AB or BA over sinus 50 degrees, BA over sinus 50 degrees equals to BD over sinus 80 degrees. Then again, according to the law of sines, this triangle ABD, the following version is true. BA over sinus 50 degrees equals to BD over sinus 80 degrees. We defined BA as A, and because of the fact that BA equals to BC equals to AD, therefore BC must be equal to A, and AD must be also equal to A because they are equal to each other. So we substitute BA by A, B equals to A, and we substitute 50 degrees by 90 degrees minus 40 degrees. So sinus 50 degrees equals to sinus 90 degrees minus 40 degrees. Likewise, in the other side of the equation, we have BD over sinus 80 degrees. We substitute 80 degrees by 2 times 40 degrees. So sinus 80 degrees equals to sinus 2 times 40 degrees. So now we found out that A over sinus 90 degrees minus 40 degrees equals to BD over sinus 2 times 40 degrees. In the next step, I presented to you two trigonometric identities, and we presented two trigonometric identities in this equation. The first trigonometric identity is as follows: sinus 2 alpha equals to 2 times sinus alpha cosine alpha. The second trigonometric identity is as follows: sinus 90 degrees minus alpha equals to cosine alpha. So according to the second trigonometric identity, we get that sinus 90 degrees minus 40 degrees equals to cosine 40 degrees. Well, according to the first trigonometric identity, this trigonometric identity, we get that sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. Repeat again. According to the first trigonometric identity, sinus 2 times 40 degrees equals to 2 times sinus 40 degrees times cosine 40 degrees. So this equation equals to A over cosine 40 degrees over BD, or 2 times sinus 40 degrees times cosine 40 degrees. Here we have cosine 40 degrees on both sides of this equation, so cosine 40 degrees will get cancelled, also cancel cosine 40 degrees. In this side of the equation we are left only with A, while on the other side of the equation we have BD, we are left with BD over 2 times sinus 40 degrees. So in total we found out that BD equals to 2 times sinus 40 degrees. Here we multiply this equation by 2 times sinus 40 degrees. We found out that the missing side BD equals to 2A times sinus 40 degrees. This is the missing side BD. This equals to 2A times sinus 40 degrees, and it's there. In the next step, actually, what is the size of this missing angle BDC? On the drawing, it is very easy to see that angle BDC, this angle in total equals to 80 degrees minus 50 degrees, that is 30 degrees. We define this angle BCD as beta, and then we implemented the law of sines in this green triangle BCD. According to the law of sines, in this triangle BCD, BC over sinus 30 degrees equals to BD over sinus beta. So in the green triangle BCD, according to the law of sines, BC over sinus 40 degrees equals to BD over sinus beta. BC is A according to our definition, and sinus 30 degrees is 1/2. So in total, in this side of the equation, we have A over 1/2, and it equals to BD. BD is 2A times sinus 40 degrees over sinus beta. A over 1/2 is 2A, And the other side of the equation, we have 2a times sinus 40 degrees over sinus beta. So in total, if we found out that 2a equals to 2a times sinus 40 degrees over sinus beta. Here we multiply this equation by sinus beta, and we found out that 2a times sinus beta equals to 2a times sinus 40 degrees. Here we have 2a on both sides of this equation, so 2a will get cancelled. After we cancel 2a, in this side of the equation we left only if sinus beta equals to sinus 40 degrees. If sinus beta equals to sinus 40 degrees, it means that beta equals to 40 degrees. But we have another solution for beta. According to the first trigonometric identity, that said that sinus alpha equals to sinus 180 degrees minus alpha. So sinus 40 degrees must be equal to, according to this trigonometric identity, sinus 40 degrees must be equal to sinus 180 degrees minus 40 degrees. But 180 degrees minus 40 degrees is 140 degrees. So if you found out that sinus 40 degrees equals to sinus 140 degrees. But we already found out that sinus beta equals to sinus 40 degrees. And according to this equation, sinus 40 degrees equals to sinus 140 degrees. So it's here. Sinus 40 degrees equals to sinus 140 degrees. And from this equation, sinus 140 degrees equals to sinus 40 degrees equals to sinus beta, we will derive that sinus beta equals to sinus 140 degrees. Those two sides of the equation are equal to each other. So sinus beta equals to sinus 140 degrees. If sinus beta equals to sinus 140 degrees, it means that beta equals to 140 degrees in its sides. This is according to the second solution for beta, but according to the first solution for beta, beta equals to 40 degrees. So we have two solutions for the value of beta. Beta could be equal to either 40 degrees or to 140 degrees. But if you follow the drawing of this green triangle BCD, this is angle beta. From the drawing, it is very easy to see that angle beta is definitely greater than 90 degrees. If angle beta is greater than 90 degrees, angle beta could never be equal to 40 degrees, that is less than 90 degrees. So we cancel this first solution for beta, and we took into account only the second solution for beta. That is to say, beta equals to 140 degrees in size. This is again BCD, this is equals to beta, and beta equals to 140 degrees in size. We know that the sum of the angles in triangle BCD must be equal to 180 degrees. So which angles we have in the great triangle BCD? We have 30 degrees plus 140 degrees, plus this angle is angle DBC. In total, the sum of those angles must be equal to 180 degrees. So in the great triangle BCD, 30 degrees plus 140 degrees plus the missing angle DBC, in total must be equal to 180 degrees. 30 degrees plus 140 degrees is 170 degrees. So 170 degrees plus the first missing angle DBC, in total must be equal to 180 degrees. Here we subtract 170 degrees from this equation, and find out that the missing angle DBC equals to 180 degrees minus 170 degrees is 10 degrees. So here this is the missing angle DBC. This is equals to 10 degrees in size. Our task is to find out the size of this angle ABC. This equals to x. So in total, the size of this angle ABC equals to 50 degrees plus 10 degrees. This is 60 degrees. So angle ABC is equal to angle x. In total, it is equal to 60 degrees in size. So finish to repeat on the first question. The next step, I repeat on the solution of the second question on both methods. In the second question, our task was to find out the length of side AD. This is equal to x. So we have to find out the length of line segment x. So in the drawing, we have quadrilateral ABCD. Those two angles are both right angles. We also know that AB equals to BP. The short line segment DP equals to 1 unit in itself. Line segment PC equals to 4 units in itself. Again, our task is to find out the length of this side AD is equals to x. So we have to find out the length of line segment x. So we start with the first method. So first of all, we join points B and D together by side line. By joining points B and D, we divided quadrilateral ABCD into two right angles. We have the upper right triangle DAB and the lower right triangle BCD. So we implemented the Pythagoras theorem on those both right angles. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this right triangle ADB, according to the Pythagoras theorem, dB squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. Repeat again, this upper right triangle ABD, according to the Pythagoras theorem, BD squared, that is the square of the hypotenuse, equals to AB squared plus AD squared. BD is the missing hypotenuse, so we leave it as it is. So it is BD squared equals to AB squared. AB squared. AB is the missing side, so we leave it as it is. So it is AB squared plus AD squared. AD equals to x, and therefore AD squared is x squared. X is the line segment that we are looking for in this question. So according to equation 1, we should find out that BD squared equals to AB squared plus x squared. Likewise, we implemented the Pythagoras theorem on this right lower triangle DBC. The lower right triangle DBC, DB squared, that is the square of the hypotenuse, equals to BC squared plus DC squared. DB squared, that is the square of the hypotenuse, equals to BC squared plus DC squared. Okay, again, according to the Pythagoras theorem, the right lower triangle DBC, DB squared, that is the square of the hypotenuse, equals to BC squared plus DC squared. DB is the missing hypotenuse, so we leave it as it is. So it is DB squared equals to BC squared. BC is also the missing side, so we leave it as it is. Plus DC squared. DC is 1 plus 4, that is 5. Therefore, DC squared is 5 squared, that is 25. So in total, according to equation 2, we should find out that DB squared equals to BC squared plus 25. So we have two different equations for DB squared, equation 1 and equation 2. Therefore, we get the equation 3 that says that dB squared according to equation 1 must be equal to dB squared according to equation 2. dB squared according to equation 1 equals to AB squared plus x squared. And it must be equal to BD squared according to equation 2. BD squared according to equation 2 equals to BC squared plus 25. So in total, according to equation 3, I should find out that AB squared plus x squared equals to BC squared plus 25. The next step is implement the Pythagoras theorem on the great right triangle PBC. According to the Pythagoras theorem on the great right triangle PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus BC squared. Repeat again. According to the Pythagoras theorem, in the great right triangle PBC, PB squared, that is the square of the hypotenuse, equals to BC squared plus BC squared. PB is the missing hypotenuse, so leave it as it is. It is equals to BC squared. BC is also on the unknown side, so leave it as it is. So it is BC squared plus PC squared. PC is 4, therefore PC squared is 16. So to that, according to equation 4, we should find out that AB squared, according to equation 4, we should find out that AB squared equals to BC squared plus 16. But according to equation 3, we already found out that AB squared plus x squared equals to BC squared plus 25. So we can substitute AB squared in this equation 3 by BC squared plus 16 from equation 4. We did it, and AB squared is BC squared plus 16, and we have plus x squared equals to BC squared plus 25. So in total, according to equation 3, I should find out that BC squared plus 16 plus x squared equals to BC squared plus 25. Here we have BC squared on both sides of this equation 3, so BC squared will be cancelled. After we cancel BC squared, on the side of the equation we left only with 16 plus x squared, while on the other side of the equation we left only with 25. So in total, according to equation 3, I should find out that 16 plus x squared equals to 25. Here we subtracted 16 from this equation 3, and found out that according to equation 3, in the side of the equation we left only with x squared. On the other side of the equation we have 25 from 16, that is 9. So in total, according to equation 3, I should find out that x squared equals to 9. Here we took out the equation, and I found out that x equals to the square root of 9, that is 3. So this is the missing side AD equals to x, and x equals to 30 is left. AD equals to x equals to 30 is left. So we finished with the repetition of the first method. The next step I repeat on the solution according to the second method. We find out therefore far side AD is equals to x according to the second method. We repeat on the solution according to the second method. In the second method, we did the construction. That is to say, we extended line 7 DC by 4 units. Again, we extended this side DC of this coordinate ABCD by 4 units. So here we have this line segment equals to 4 units in its length according to our construction. We define the extended line segment, the edge of the extended line segment. This point is point Q. DC is one side of quadrilateral ABCD, therefore it is absolutely a straight line. When you extend a straight line by straight line, the result DQ is also a straight line. So DQ is a straight line. If you focus on the upper side of this straight line DQ at point C, here the sum of the areas must be equal to 180 degrees according to all three. All three said that the sum of the areas from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line DQ at point C? We have this angle that is right angle according to what is given us in the question. Plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees and inside. In the next step we join points B and Q together by straight line. By joining points B and Q, we can then the right triangle BCQ. So in the next step we prove that those two right triangles can go into each other according to sine angle side rule. So why those two right triangles can go into each other? First of all, PC equals to CQ equals to 4. They are both equal to 4, therefore they are equal to each other. Likewise, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, side BC is a common side that belongs to both triangles, so we can write down that BC equals to itself is a common side that belongs to both triangles. So we found out that those two right triangles can go into each other according to side angle side rule. And again, the two right triangles can go into each other according to side angle side rule. So all the dimensions can go into each other according to side angle side rule. We have found out that those two sides and the angle that is included between those two sides in this right triangle PBC are corresponding equal to those two sides, and the angle that is included between those two sides in this right triangle BCQ. Therefore those two right triangles can go into each other according to side angle side rule. And from the fact that those two right triangles can go into each other, we will derive that the corresponding sides must be also equal to each other in their lengths. The corresponding sides are the two hypotheses. That is to say, PB equals to BQ. PB equals to BQ. According to the rule, the corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the corresponding sides, that is to say PB and BQ, must also equal to each other in their lengths. And we know that we just right now found out that BP equals to BQ. But according to what is given as a question, AB equals to BP. We found out that PB equals to BQ because the two right triangles can go into each other. But according to what is given as a question, AB equals to PB. So we can write it that AB equals to PB. And from this equation, AB equals to PB equals to BQ, we will derive that those two right segments AB, PB and BQ, they are all equal to each other. So in the next step, we did the construction, that is to say, we draw a circle around point B in such a way that point B will be the center of the circle and BA will be the radius of the circle. So this is the circle that we draw, and BA is the radius of this circle according to our construction. So we define the radius BA as R. and because of the fact that AB equals to BP equals to BQ, and BA is the radius of this circle, and therefore BP and BQ must be also the radius of this circle, is equals to R. And the definition of a radius, the radius of any circle starts from the center of the circle and ends on the point on the circle itself. And therefore those three radii, AB, BP, and BQ, their edges lie on the circle itself, or in other words, the circle must pass for these 3 points A, P, and Q because of the fact that those two line segments A, B, BP, and BQ are all the radius of the circle. And therefore, the circle must pass through points A, P, and Q. So, this gives us a question that because of the fact that angle DAB equals to 90 degrees, it means that DA is perpendicular to AB. So according to what is given as the question, DA is perpendicular to AB. But according to our definition, AB is the radius of the circle. So DA is perpendicular to the radius AB. DA is perpendicular to the radius AB. This is the sign of perpendicular. DA is perpendicular to the radius AB. This is equals to R. So therefore DA is the tangent to this circle at point A. DA is the tangent to this circle at point A. So if we focus on the common sum point D, from the common sum point D we have tangent DA, that is tangent to this circle at point A. Likewise, from the same common sum point D we have secant DQ that cuts the circle at 2 points, P and Q. DP is the external part of secant DQ, and the secant in total equals to DQ units in itself. So all the requirements of full tangent secant theorem are satisfied, and therefore we can implement here tangent secant theorem on this common sum point D. So a bit quicker on tangent secant theorem. According to tangent secant theorem, if a tangent and the secant are drawn to a circle from the same external point P, this is the common sum point P. From the common sum point P, we have tangent PA, that is tangent to this circle at point A. Likewise, from the same common sum point P, we have secant PC, that cuts the circle at 2 points, B and C. PB is the external part of secant PC, and the secant in total equals to PC units in itself. Again, PB is the external part of secant PC. So in this domain, the following equation is true. The square of the tangent's length equals to the product of the secant's all length and its external part. The length of the tangent squared is PA squared, and it is equal to the product of the external part times the length of the secant in total. The external part is PB, the length of the secant in total is PC, and the product is PB times PC. And the product PB times PC equals to the length of the tangent squared. So total we should find out that PA squared equals to PB times PC. PA squared equals to PP times PC. So we can implement tangent secant theorem in our domain. Likewise, in our domain, from the common sum point D, we have tangent DA, that is tangent to this circle at point A. Likewise, from the same common sum point D, we have secant DQ, the external part of secant DQ is DP, and the secant in total equals to DQ. The product of the external part times the secant as all is dP times dq. And it's equals to the length of the tangent squared. That is dA squared. dA squared equals to dP times dq. But again, according to the tangent secant theorem, if you focus on the common sum point D, the following equation is true. dA squared, that is the length of the tangent squared, equals to dP times dq. dp is the external part of secant dq, and dq is the length of the secant in total. The product of the external part times the length of the secant in total equals to pa squared. Equals to dA squared. Equals to dA squared. This is the length of the tangent squared. dA equals to x, and therefore dA squared equals to x squared. dA squared equals to x squared. dP is 1, dQ is 1 plus 4 plus 4, that is 9. So total x squared equals to 1 times 9. 1 times 9 is 9, so x squared equals to 9. You have to go out of the equation and find out that x equals to the square root of 9, that is 3. So the length of this side AD, or right side AD, or tangent AD is equal to x, and x equals to 3 units in its length. And again, AD that equals to x is equals to 3 units in its length. So in both methods, we have to find out that the length of this side AD is equals to x is equals to 3 units. Okay, thank you very much.